Yeah, things seem to be strange. Okay, it's some technical things. It's really not expected. I think I better rather I try to fix it afterwards because I worried once I change something, maybe nothing will work. You will never know for computer. Really, to mess up a thing, we need a computer. Once it's messed up, it's really messed up. Okay, so I will continue. The worst thing maybe it will stop again. Okay, but then I can relog it. It seems it will work that way. So really sorry about that. I really out of my control. Okay, it could be due to the problem last week because of the change of password by university system. That may cause the problem because I did not try it afterwards. Actually, I tried to use Zoom, but it's not a long time, only a few minutes. Okay. Okay, so let's continue. We'll see what's going on. Okay. What will happen? I mean. All right. So the reason of discussing big O notation is we need it very often in computer science, especially when we analyze learning time of algorithm, in particular when we consider divide and conquer algorithms. So typically, in order to solve a problem, we recursively divide the problem into few parts, maybe two parts, and recursively solve the problem. Then for each part, we divide it again into smaller problems and keep on dividing. So that's the basic idea, divide and conquer algorithm. Then in terms of running time, typically we will get an algorithm, a recurrence relation, such as the following. So we get a recurrence relation like this. All right. Then for small n, we have boundary condition, maybe C1 is a constant. So C is some constant. This one can be also written as big O of 1 for constant, bounded above by constant. Okay, so be familiar with this notation. This one means it's bounded above by a constant. The function has upper bound. All right. Okay, so typically this kind of recurrence relation we'll see in computer science, and we need to find out this T of n. We want to know the growth rate of T of n. So T of n typically is the running time. The growth rate. So instead of the precise solution of Tn of n, we only need to know the growth rate. So that means in terms of big O notation, we want to find the function above by some simple function. Right? So we need to deal with this kind of recurrence relation. Now, in terms of big O notation, one nice thing again is we can be lazy. We can ignore these functions. This function called the ceiling function. This makes things quite complicated. So in case n is not, if n is the power of b, then it's okay. Otherwise, this number may not be an integer at all. May not be an integer. It's not an integer. So that's increase the complexity in dealing with that. But with big O notation, it's easier to deal with this one. So we can ignore the ceiling or floor function. So instead, what we need to do is consider this recurrence. So equality actually, this inequality can be also written as equality once we use big O notation. So here A, T, N over B. But here typically it's some big O notation. So instead of this one, typically what we'll see is the following recurrence relation when we analyze running time or divide conquer algorithms. So here we divide the problem into 8 parts, each of size n over b. Okay. Now there's some subtlety here. Actually, we are kind of abuse the definition of big O notation. In big O, the definition of big O notation, this function should be a function of integers. But it actually does not matter. If even we allow this one to be real number in terms of growth rate, it still holds. So very often we abuse this notation. All right. Also, another thing I want to mention, very often people abuse notation. Sometimes when you see that Tn equals say big O of n squared, very often you will see it even in computer science literature. When you see this one, actually the order may mean this one is theta of n squared. It has become a convention. Sometimes we abuse this big O notation. Use big O and theta. It happens very often in practice. Okay, so this one is not found, but people always abuse it. Use this one as type bound. So precisely we should use theta instead of big O, but you see it very, very often people abuse this one. Okay, that's another point I want to mention. All right. So what we need to deal with is to solve this recurrence relation in terms of big O notation. So solve this one in terms of big O notation. That's our piece. In big O notation. So we try to solve this recurrence relation. How can we do it? All right. Okay. So that's our task. Before we discuss how to solve this one, let me give you a few examples, very important examples in algorithms. For computer science, it's very important. For merge sort, sorting algorithm, we have Tn equal to Tn over 2 linear. So this part is time for doing everything when we combine solutions. So that's cost. For merge set, when we merge to sort the list into one, that's time it takes. All right. So for this difference, we have Tn equal n log n. That's time for merge sort. Now for multiplication of two n-digit numbers, when we multiply two n-digit numbers, of course, it takes n squared time, but we can use divide and conquer method to do better. And you will learn from algorithm course, maybe next term or next year. For multiplication, we can obtain a divide and conquer algorithms that are this time as a consist recurrence relation. All right. For this one, the solution will be n to the power of 1.59. So instead of n squared, it's better. It's 1.59. All right. One more example, matrix multiplication. For matrix multiplication, one can get the following recurrence based on divide and conquer idea. And this one will give us running time. Once we solve this one, that's n to power 2.81 instead of n cubic. So all of them have this form. So it's very important now. How can we solve this recurrence relation? Okay. Okay, so that's out. Okay, something come up. Let's see. Okay, so far it's okay. All right. The target is to solve this recurrence relation. So how can we solve it? In general, actually, it's not easy because this part, it's there depends this function. As we know from recurrence relation, in general, we don't know how to solve linear recurrence relation when it's non-homogeneous in general. All right. Now this part is non-homogeneous. If without this one, it's very easy. If we should look at this one, without this one, okay. So let's have a taste of this recurrence relation first. Okay, so let's make a comparison with linear recurrence relation. So let's see. Yeah. All right. So for linear recurrence relation, we have maybe when I consider first order, we use this one as use A, I think, right? Maybe A. So compare this one with this one. So this one is having this form, this non-homogeneous first order recurrence relation. So in general, we don't know how to solve it. It's difficult. But when this one is a polynomial function or polynomial function times exponential function, we do have a general method to solve it. That will be helpful here. All right. So now the one special case of this one is when it's homogeneous without this part. Then it's very easy. We can keep on extending it, right? So that's what we get eventually. Roughly an, okay. So here, if we don't have this one, this is very easy to solve. So we just a squared t and b squared, right? Then an a cubic t and b cubic. So eventually, how many times do we need to go? It's log base b n. So then here will become 1. So that's very easy to solve. Now the problem is we have this one. So that makes things difficult. So that's called the problem. Otherwise, it's just this one. We'll come back to the connection between this one and this one. Yeah, it will be very useful. Since we know how to solve this linear recurrence relation, that will be helpful to get solution for this one. So as I said, in general, it's very difficult. But for special case, when this function is a polynomial function, then we do know how to solve it. So let's focus on the following special case of this one. Because in practice, even if it's not a polynomial function, we can consider it above a polynomial function. As it's grows slower than polynomial than exponential function. Okay. So suppose this part. So let's look at n. So it can be n cubic, or maybe n cubic log n. So in this case, we can always replace it by n cubic, say, in this case. So very often we need to deal with the function fn here. This is polynomial function. So for this purpose, we'll concentrate on polynomial functions, and that will be enough for at least 90% of us. All right. So we consider in this form. Zero can be okay. Its constant could be okay. So it can be 0. So A, B are integers, non-negative integers, and B can be real number. So this one can be real number. Any real number here. Okay. So for this particular case, we do have a formula for this one. So it's easy to remember. Yeah. And I will tell you how we obtain this formula. So I give you formula first, then I'll tell you how we obtain this formula. So that means we'll prove it. Why this one is the case. Okay. So let's see. Let's go back to the solution of this part. So let me write down again. So this part. If we just have this one, then we discussed earlier, solution will be order n to power log d. That's a solution. All right. Now look at this one. If we compare this one to a recurrence relation, non-homogeneous one, the solution contains two parts. One is homogeneous part. One is homogeneous part, which is this one. One is a particular solution for this one. That's a non-homogeneous part. So that one is for the current relation, our solution always looks like this one is of this form. Remember, last week when we discussed it, this homogeneous part is an plus a particular solution. The situation is very much like this one. Solution will be summation of these two. All right. Now, based on property of Bigot notation, summation of this one is maximum of them. So this one is maximum of these two. All right. So what happens is solution of this one. Let me leave this one go. Okay. All right. Very depends on we compare these two. The big one dominates. So we compare D with log DA to see which one is bigger. The same as compare this one B to power D and A. Compare these two. The same thing. Okay. Okay. So let's just compare these two. Okay. So if D is bigger, this one dominates with n to power D. Now if this one is bigger, then this one dominates. This one is the leading term, so we have n to this power. Now there's a situation when these two are equal. What does that mean when they're equal? Remember when we discussed the non-homogeneous recurrence relations, when the characteristic function here is a root of, so for linear recurrence, we have s of n here, exponential function. When this s is a root of a characteristic function equation of a non-homogeneous part, then the general form here will multiply it by n. So for this part, same thing happens. So that will be n to power d multiplies. It's not n. You will see why is this log n. Okay. Later on, I will tell you why it's log n. Actually, this log n same as n. So there are three situations, depend on which one is bigger. When d is bigger, it's n to power d. When d is small, then it's log b to a. Suppose that polynomial function. Okay. And when these two numbers equals, we need to multiply it by log n. So that's where we get n log n for merge sort. For merge sort, we get n log n. For other two, we have this one. For matrix multiplication, for multiplication, we have this one. All right. So that's the formula. Only three cases. Yeah. I want you to remember this one. Really remember this one. Okay. What you compare is these two numbers, log A and D, or A and B to power of D. Compare these. When in algorithmic course, when we discuss divide counter algorithms, we'll see the meaning of these things. We will have a better understanding of the connection of this number and this number. Okay. For the time being, you only need to compare these two numbers or equivalent to these two numbers, D or log BA. Maybe it's easier to log BA and D because here it's AB, the log BA, okay, instead of this one. These two are more closer here, more close here, okay? All right, now I will show you why this one is the case. All right, we try to solve this difference relation to obtain this formula in two different ways. I'm sure we will have time for first one, but for next one, I think we still have time. Okay. Should be able to use both approach to get this one. The first approach is do it directly, use iteration method. The second approach is use non-homogeneous recurrence relation. Okay. All right. So let's try to solve it directly. Use iteration method. All right. So for this one, it can be written as maybe put a C here. C. Big O notation of this one means when n. So this formula. Okay. Sorry, I forgot to mention the meaning of this formula. This formula means when n is large enough. So this one means okay. So here without big O notation, that's the meaning of this formula. So this is very recurrent relation. So we can try to solve it directly using iteration methods. So one way is to organize things as follows, as I demonstrated many times. So put A, P, and B on this side, then replace n by n over d, n over b. Okay, so we get a squared t and b squared plus c. So n is divided by b. All right, so iteration method. Okay, so here we have a cubic t and b squared upon here squared. Okay. Oh, no, it happened again. Okay. In 10 minutes. So in 10 minutes, you will stop again. Oh, shit. Sorry. Sorry, my luck for my Russian. Okay. It will stop in 10 minutes. I will log in again. Okay. All right. So keep on doing it. Eventually, you get here a log b n t 1. Yeah. Okay. So here actually is yes. Okay. Plus c uh, b n I'm not 100% sure whether it's -1, +1 or something, but it's close enough to be okay. So something like that. Then when you sum them up, so these thing cancels. That does not matter. These thing cancels. All right. So eventually, what we get Tn a log Bn. So this one is a constant. All right. Now plus the summation of C, the summation n b I our d sum I equal 0 to log Bn minus 1, I think. Okay, so we can explore this part now. So what we have is Tn is O of A. So I see homogeneous part here already. Okay, homogeneous part. What's this part? Okay. So this summation whether converges or not depends on value A and this one. Depends on the I found this I. So this part, this sequence. So actually ND can be taken out. So let me rewrite it. It can be rewritten in this way. Okay, so here, actually, if you want to use big O notation, can even change this one to big O of ND and this one. Okay, so really depends this sum. Oh, sorry, I forgot an A. Here I forgot an A here. Somewhere I forgot an A. There should be an A here. Where did I forget this A? There is A. This one should be A. So somewhere I forgot this is A. Oh yeah. Well, when I when they expand it, I forgot this A. So there are A here. I forgot. Yeah, otherwise it does not make sense. There are A here. But the tedious thing when we expand this term Tn equal A T N B plus C and B. When I expand it, I forgot this A. When I times this A, here equal A squared. Here I forgot, should be CA. I forgot this one. Okay, that's why I forgot this A. Okay. All right. All right, now depend this summation. So let's count this case when A equals log B. And, let's see. No, that's fine. Let's see. The summation. B. Did I say log n? BD, sorry. I mean BD. When A log B equals D. That's what I mean. I did not write n, I think, right? When this one equals, when this one equals, Then this one, there are log n terms. Who's doing that? Perhaps I could make some students a co-host in case there is this kind of disruptive ideas, behaviors, we can stop it. So I try to assign some students to act in my behalf to stop this kind of things. Okay. Let's see. I messed something up. D. No, that's when I do algebra, often. Yeah. Okay. That's correct one. Okay. Yeah, sorry, for the algebra part, very often that thing up. Okay. So the formation look like the a over b to power d, here is I what okay. Now when this one equals, that means a equals b to power d. Then there are log n terms. The number of terms is 1 plus 1 plus 1 log n terms. So each power to 1, 2, here log bn minus 1. So when this one is 1, then number of terms here gives us log n. So that's why we have the middle case, n power d times log n. All right. Otherwise, the sequence converges to a constant. Either the sequence converges to a constant. It's a constant. One is bigger, one is smaller, but it's a constant. Therefore, the bigger of these two will dominate. That's what happens. All right. So we can solve it directly. Yeah, funny. It's if you try to do it in this way, you then need to be careful. As what happened here, I made some mistakes when I do these manipulations. There's a joke about a mathematician. When mathematician very often says A, but it's right B, actually what he means maybe C. Because somehow in his mind, A, B, C, these things are same, just a symbol to denote different things. So no difference from mathematical point of view.
China.
It's just a joke. Okay.
China.
Who's that guy?
You go over to China. Love them.
Yeah, it's no, the problem system. I set it to mute everyone, but each time it's automatically cannot take that option for some reason. I don't know. Okay.